and we can look at the effect of the vacuum bath on general relativity, on gravity, and we see that it leads to an accelerated expansion of the universe, precisely as we observe. This is the good news. The bad news is that the expected rate of this acceleration, based on the amount of vacuum energy or the amount of vacuum bath that fills the whole of the universe, is way, way, way too large. And the error is not just a factor of 2 or a small computational error that I can put under the rug. The discrepancy is actually of 28 orders of magnitude. This is the biggest discrepancy, the biggest embarrassment in the whole history of science. And it's been known for a century. And this is such an embarrassment because on one hand, you have general relativity that has never betrayed us, that predicts everything we have observed, including gravitational waves and black holes, to an impeccable precision. And on the other hand, we have this vacuum bath coming from particle physics that has also never betrayed us. It's been detected the Higgs, and we have understood the standard model of particle physics to an incredible precision. Both of them have never betrayed us, and both of them correspond to the pillars of modern physics. And yet we put those two things together, and we get the biggest discrepancy in the whole history of science. So what went wrong? I don't know. I really don't know. Is it our understanding of this vacuum bath or how the fundamental particle affect this vacuum bath incorrect? Or is its effect on gravity on the larger scales of the universe incorrect? In fact, Einstein's theory of general relativity has never been probed on such large scales. So that's a possibility. Very few possibilities have been proposed. And the one I like to raise, and it's a crazy one, but I'm going to raise it anyways, is that maybe rather than needing to take all of this vacuum bath quite so seriously over the whole history of our universe, over billions of years, and over the whole volume of the universe, gravity doesn't need to be quite so serious after all. The possibility I like to raise is to say, hey, gravity, time to relax. In Einstein's theory of general relativity, the graviton, like the photon, is a massless particle, which means that it has an infinite range. What this means is that technically, two objects, like two galaxies, located on the other side of the universe from one another, that is located 10,000 million trillion kilometers away from one another, still exert a small gravitational attraction on each other. Even more remarkable, to understand the dynamics and the dynamics of the whole universe, we also need to account for all of the vacuum bath that fills the whole of the universe. But maybe this is just too much to ask. Could it be that the gravitational attraction that we share, you and me, I hope you can feel it, and that we share with the Earth, and with the Sun, and with the galaxy, and even with our local cluster of galaxies, is only present because we are sufficiently close to one another? Could it be that we don't share the same gravitational attraction with objects and with the vacuum bath located on the other side of the observable universe, some 10,000 million trillion kilometers away from us? In practice, what it would mean is that we would need to weaken the range of the gravitational force. I can have a demonstration here on how it looks like. I'm sure you've seen such a thing before, like a trampoline surface. You put a mass at the center and you see how it deforms the structure of this surface. This is more or less what we had at the beginning with a few caveats. What we like to do here is restrict the range of the gravitational force such that if you have a mass, it only affects some given neighborhood. And so two masses located very far away from one another, technically they would stop having the gravitational attraction on one another. More importantly, we now need to account for all of the vacuum bath of the Higgs and all of the other fundamental particles to account for the dynamics of the universe and this huge accelerated expansion of the universe. So what we need to do is understand how to restrict or weaken the range of the gravitational force. But that's easy. Nature has already told us how to do that. Nature has already told us that the weak force is weak because the Higgs mechanism has weakened the range of this force by giving a mass to the fundamental particles that carry this force, the W and the Z boson. So in making the W and the Z boson massive particle, we have restricted the range, the operation of the weak force. So in principle, all we need to do is the same thing for gravity. Either we need to restrict the range of gravity from a point of view of Newtonian force if you want, or at the more fundamental level, what we really need to do is understand how to give the graviton a mass. And this is an extremely natural question. It's so natural that even Newton himself contemplated this possibility at the level of weakening or limiting the range of the Newtonian gravitational force. And many other amazing scientists since then, including Laplace. And then when we understood that gravity could also be carried by a fundamental particle and that was related to Einstein's theory of general relativity, and we understood that limiting the range of gravity was really corresponding to giving a mass to the graviton, this has been explored by many different scientists in the past century, including by Pauli, who's one of the founders of quantum physics, including Salam, who's the same Salam responsible, one of the founder of the electroweak theory and one of the fathers of the standard model of particle physics. And many other amazing scientists since then have been exploring the possibility of thinking what it would mean to restrict the range of gravity or give the graviton a mass. But this possibility has always been entirely refuted. And not because it contradicts observations. Quite the opposite. It could help with observation of the accelerated expansion of the universe and reconciliate the amount of energy contained in the vacuum bath and its expected contribution on the accelerated expansion of the universe. Now, this possibility has always been entirely refuted because it was impossible to make it work theoretically. Looking at the literature for the past century, on the topic, this is what you would read. No way, inconsistent, impossible, instability, and what I love most of all is plagued by a ghost. Now, a ghost, this is a scientific terminology, this is not me inventing for once. A ghost is the most terrifying thing that you can ever imagine. A ghost is a particle with negative energy, which would make the whole universe and you and me and everything living in it, even the very structure of space and time, decay instantaneously. So clearly, if we have a theory of gravity with a limited range, or a theory of massive gravity, we need to find a way to get rid of this ghost or to trap it. And this is what has been made possible to these two incredible gentlemen, Gregory Gabadatsi and Andrew Tolley. In practice, the trap that we engineered looked much more like an Asian stare or a Penrose stare, where we trick the ghost to live in a constrained space from where it cannot exit and do no harm. This is symbolic. The real proof uses lots of mathematics, but the result is the same. And to my mind, that trick was pretty cute in itself, but we soon came to realize that having one mathematical bulletproof proof for the absence of this ghost and the consistency of the theory of massive gravity would be enough. But soon enough, we realized that was never sufficient to convince the rest of the scientific community. To be sure, science and mathematics in particular, doesn't lie. So if something is proven in one mathematical language, it has to be true. But even in science, there's lots of different scientific culture and different mathematical architectures and scientific arguments that people feel more or less comfortable with. So over the years, every time a new colleague had a different perspective, we were compelled to learn the language and translate a logic and arguments to their way of thinking. And we have to repeat this process years after years after years until there remain no unanswered question. A theory about massive gravity wasn't judged by a closed jury of 12 peers. It was judged by the whole multicultural scientific community. Overcoming that process, though, was never the aim. It was just the start of the journey, one which would finally allow us to test gravity, compete it with Einstein's theory of general relativity. So if the graviton could have a mass after all, what would be its value? It'd be tiny, 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 tiny. We wouldn't want this distance to be as small as the subatomic scale, like the weak force, for instance. That would be just silly. We need those distances to be very, very large, which means the mass of the graviton to be very, very weak. If we put the graviton in a normal particle scale, if we wouldn't measure anything. It would be lighter than all of the massive particles that we know of, including the neutrino. So instead, we need very precise instruments to measure the mass of the graviton. And gravitational waves interferometer may be able to play that role in the future, including the LISA space mission that will allow us to detect gravitational waves with very long wavelength, very small frequency. If you think of them as color, it would be going very much towards the red and beyond. For a specific event, on the top is the type of signal you could expect to have if the graviton had no mass. While at the bottom is the type of signal you would get if the graviton had a large, large mass. The effect is very much strengthened because we're dramatizing it. We're making it very large. You see that the signal appears more compressed because gravitational waves of different frequency or different color travel at different speed. So in future experiments, by comparing our expectations with actual observations, we should be able to put a constraint, an even better constraint, on how light or heavy, massive I should say, the graviton mass is. Whether the theory of massive gravity developed by my collaborators and I will survive the test and be relevant at all for nature is for future generations to tell. But the possibility is now open. For now, I just want to contemplate the fact that right now, in this room, it can be day or night, I don't even know, clear or cloudy, I don't know, but gravitational waves are reaching us from the depth of the universe. And with them, they carry the most precious and important messenger there is. Detecting them and understanding them will allow us to understand if and how we connect with objects on the other side of the universe, some 10,000 million trillion kilometers away from us. They will allow us to understand whether the infinitely small fluctuations from all of the particles that we know can have an effect on the biggest scales of the universe, possibly dictating its acceleration. And to me, this is remarkable because gravity is the weakest force there is. While we have detected gravitational waves, we will never, ever detect a single graviton like that, not per se. But what fascinates me the most about her is that she perfectly illustrates how the most subtle and discrete and shy particle there is can, through nothing other than sheer persistence over the billions of years of existence of our universe, and cohesion with a gazillions of friends, be the most important element in the whole universe. She's the one setting space and time alive, the one responsible for the whole evolution of the universe, the creation of a galaxy, the formation of a home, and will be the one ultimately determining our own fate, that of the whole universe, and everything living in it. So I'll stop here. Thank you.